So I better mark this one as chapter 1 problems. Number 1. Which of the following is an example of a quantitative observation? Remember the difference between quantitative and qualitative. When you think quantitative, think numbers. Qualitative is just a descriptive term. So the temperature of the liquid is 60 degrees. That's definitely quantitative. Rest of them are qualitative. Notice sometimes in multiple choice tests, you'll have unique answers all the way through. And sometimes you'll have maybe 2 or 3 at the top, and then the last 2 will say none of the above or 2 of the above. Those, I call those squirrely answers. When you see those, that just means that you've got to look at all of the ones above in order to make a choice to eliminate the ones below. Everybody familiar with multiple choice test taking techniques? Yeah, I figured by this time you should be. Okay, so that one is D. D's the answer for that one. Now, if I'm boring you, we can skip some of these. How about 2? Generally observed behavior that can be formulated into a statement, sometimes mathematical in nature, is called what? That's a law. A law. As opposed to what? A theory, right? A law just says what happens. A theory under certain circumstances. A theory tries to explain why it happens so that we can modify it and broaden its application. So that one is also D. All right, how about this? We want to put these prefixes in order from smallest to largest. What I would do is I would look at what we have available and just list them up there. So the first one, we've got nano. And then we've got milli and centi. And then we have kilo. That was for A. Let's look for unique ones. We've already got milli. I'm looking at B now. Nano, centi, kilo again. Kilo, centi, nani, milli. Kilo, centi, milli. It looks like the same ones in all of them, doesn't it? We just have 4. All right. So which one modifies the base unit to make it smaller? Which one would be the smallest of those? Nano. I heard a whisper back there. Right. So a nano is 10 to the minus 9th, right? So that's the smallest one. This one's going to be less than any of these others. This one, milli, is how much? 1,000th of, 10 to the minus 3. Centi. We're still in good order. Centi is 10 to the minus 2. And kilo is 10 to the 3rd. Okay. So A is the right answer. They're all in the right order. Okay. Now those aren't the only ones. We have other possibilities. But for this question, that's as far as she goes. How about this one, number 6? 8.1 kilogram. We're given that information contains how many grams? What type of problem is this? You can give me the common name or the fancy name. The fancy name is dimensional analysis. The common name is unit conversions. We want to convert kilograms to grams. So do we have a factor that will do that for us? When you want to go from here to here, this has to be in the numerator at some point. This has to be in the denominator because we're canceling this one and leaving this one behind, correct? Okay, so there is a ratio we know, grams to kilograms. How many grams are in the kilogram? 1,000 grams in a kilogram. Yeah. So 1,000 times that would be 8.1 times 10 to the third grams. And just so happens that our answer is in scientific notation. B. Sometimes it won't be. You might have to change, you might have to convert it. Right. So if we converted this to standard notation, we just move that decimal place to the right. Like that. And that would be that many grams. But that's not one of our answers. Six, seven. 7, and then we'll start skipping some. Did we already skip some? Yeah, we did skip some. Convert 0.3980. 0.380 what? Meters to millimeters. Okay. We need a conversion factor. If it's available, single conversion factor is best, easiest to work with. What's the relationship of millimeters to meters? Yeah. Now you can either say so many millimeters per meters, or you can say what part of a meter is a millimeter. Either way works. As long as you got these in the right place, numerator, denominator cancel and leaves us with millimeters. So which way do you want to do it? We did it the big number on top last time. Let's say 1 millimeter is how many meters? Right, we did that earlier. 1,000th of. Right. So if we divide 1,000, a 1,000th of this is 1/1,000. That's what that is. So probably be better to do it the other way. Then it would flip and put 1,000 on top anyway, wouldn't it? So 1,000 here would be move the 3 places to the right. 3980, right? Because that decimal is there. This 0 is significant. We have to keep it. So 398.0. Notice also the unit from big to small. So the number goes from small to big. Okay, it's always the case. Just check yourself. Let's see, that would be A. Yeah. Skip down to 9. What is the measure of resistance an object has to change in its state of motion? Not a clue. That's an expression of inertia, which is dependent upon mass. A mass is a measure of substance. So the more substance you have, the more mass you have, the more it resists movement. So that would be A. Right. How about number 11? As part of the calibration of a new laboratory balance, a 1 gram mass is weighed with the following results. So we know that the standard that we're putting on the balance is that many. So that's the true value or the accepted value. Right? Okay. So if we have these 3 measurements, 1.201, 1.202, and 1.200, and this is plus or minus 0.001. We didn't talk about this earlier. This just says that we have confidence that the value that we have here is, well, we sort of talked about it. This is the uncertain value, correct? And this is the degree of uncertainty. It's really, we're bracketing it in. It's not just a wild guess. It's plus or minus. So it'd be either 0.202 or 0.200, plus or minus 0.001. That's the way you read that. Okay, so what's the question? The balance is, accurate and precise. Okay, is it accurate? Right? If we take the average of these values, you get what? That means the mean of the average. When we put a bar over something. So this is the average value. Is it accurate? No, it's not accurate. How about precise? Yeah, if it's within 0.001, then it could be 2 here or 0 here. 2 there or 0 there. They're very close. So it is precise. All right, so the best answer there is C, precise but inaccurate. That throw anybody a curve? Sort of. All right. This looks more familiar though, doesn't it? 12, 13, and 14, I think. 12, 13. No, we're just doing 12 and 13. I'll put both of them up here because they were referencing the same set of images. So for 12, which of the following figure represents a result having high precision? Well, definitely 3, Roman numeral 3, but Roman numeral 2 does also, right? Good grouping for both of them. So 2 and 3 means E. And 13, which of the following statements concerning these figures is correct? Okay. So about the only way to approach a question like this, if there are none of the squirrely answers, is to just start somewhere and keep going until you find your answer. Figure 1 represents systematic error. Oh, I think I mentioned that, but we didn't dwell on it for very long. What's systematic error? Different types of error. Systematic error is the type that gives you the same error every time. So if you've got a balance that weighs, like that previous example, it's always about 0.2 grams high, always. So we can adjust it, right? If it says 1.2, we know to subtract 0.2 from it and bring it back down to 1.001 or 1.000 or 1.002. That's systematic error. Happens the same way every time. Random error is just that. There's no pattern to it. It just is. We know it's error, but we can't nail it down. So the only way to deal with random error is with lots of replications. Make lots of measurements to try to get a handle on where the true value is, or the accepted value. So with that in mind, figure 1 represents systematic error. No, figure 1 represents random error. Those shots are all over the place. There's no pattern to it. So you can stop there and go to B. Figure 1 represents random error. Oh, wait a minute. Figure 1 systematic. Yes, figure 1 represents random error. Part B, answer B. So that's true. Then, and figure 2 represents systematic error. Yes, that is true. Based upon our systematic error is going to be in the same direction each time, which should give you good precision. You've got good precision, it's just not accurate. Okay, so we found our answer. We can stop at D. Okay. So when you're trying to deal with systematic error is pretty easy to correct for. Random error, you get into statistical analysis, and then you just have to, you try to improve your guessing with statistics. Number 16. The amount of uncertainty in a measured quantity is determined by what? Now, we didn't dwell on this. I think that's why I picked this question, because it gave me an opportunity to discuss it. You have, if you're measuring something, it could be anything. It could be mass, it could be length, it could be wavelength of light, for all I know. You've got two things, two sources of error. One is the instrument. The instrument may not be calibrated. It might be inherently inaccurate if you bought something cheap or used to do it. And then there's the operator. Many types of instrumentation require years of training and skill in order to make a correct measurement. So those are your two variables, the instrument and the observer or the operator. So if we start at the top and say both the skill of the observer and the limitations of the measuring instrument, that's it. E can't be it because we found the right one, right? None of these doesn't work. Okay. So that's A. Let's see. 17, a scientist obtains the number. Let's see what it is. 05006700. I think that's right. Okay. Let's see. If this number actually has 4 significant figures, how should it be written? So it's got zeros in it. So we got to say which of these zeros are significant, right? Because that'll determine where we start. These two are not significant. Remember, leading zeros are never significant. So we start here, right? 1, 2, 3, 4. That means we have to round to this position and we look to the right. That's greater than 5. So that means 0.05007 should be our answer. Wait a minute. I left out. Oh, I left out a 4. Start over again. 0.045, right? 45. 0.006. Okay. Same idea. We start here. 1, 2, 3, 4. Now we have greater than 5, 0.04501. There we go. So that'd be E. What would that be in scientific notation while we're here? Decimal goes 1, 2 times 10 to the what? We stored up negative powers. Right? -2. Yes, indeed. And we still preserve our 4 significant figures in the answer. Right. 20. Express this in scientific notation. Oh, wait, 1 over. All right. Let's move it 2 places again. So that's 10 to the -2. And that leaves us with 8.10. Because that 0 is significant. There's a decimal here. So this one's significant. We have to keep it. So 8.10. is to the -2 is D. -21. We're going backwards. 6.49, 10 to the -3. 6.49 times 10 to the -3. So which way would we go? If we got a negative power 10, we need to have a smaller number in standard notation. So we got to move to the left. Let's put some zeros out here for placeholders. 3 places. 1, 2, 3, right there. So we don't need that one. Don't need this one. We don't need that one. 00649. A.
Yes, sir. I
22.
did. I was calling to see if you could listen to me bitch for a second. So you remember all those really hard math problems in chemistry I had last week with those
Hello.
really exponent
Are you
numbers?
talking to me?
Those weren't on the review. So sorry, did not mean to talk.
That's okay. I didn't know if your volume was turned up loud enough that you needed to talk. Okay, let's see, 22. Express this number in common 237 times 10 to the 4th. 2.37. Let's see, times 10 to the 4th. Because we're going to move this direction, right? That's greater than 0. So we're going to have to move that direction to make this number bigger. 1, 2, 3, 4. 2, 3, 7. 0. 0. Yep. And we can't put a decimal there because we only had 3 significant figures to start with. So we're keeping 3. Now, there are some numbers, if you try to do that, you may lose a significant figure. But there's no way around it. The scientific notation is a better way to express significant figures. Let's see, 23. When we generally report a measurement by recording all the certain digits plus how many uncertain digits? Just 1. The last one to the right is uncertain. All right. 24. You asked to determine the perimeter of the cover of your textbook. What's the perimeter? The circumference of your book? Yeah. Anybody ever lived in a large city? I come from Atlanta. So when you say perimeter in Atlanta, that means Interstate 285. It goes around Atlanta. So we're going around this notebook and finding out what's the distance you would have to travel around the book. Right. So it has 39.36 length. What is that? Centimeters? Centimeters. That's a big book. 39.36 is a yard. Actually, it's a meter. No. 39.36 inches is a yard. Okay, so I'm going backwards. Scratch that thought. Except for it's still big. 2483. Okay. So what do we have to do? How many significant figures should you report? In this case, to find the circumference, you need to add 2 of these to 2 of those, right? You have this one on that side and this one on that side. So we just line them up, right? Let's pull this one down here. Let's do this one more time and do this one twice. So this has the add subtract rule for significant figures, which means you have to line up the decimals and then actually do the calculation. So what is this? 3 times 6 is 18. Carry the 1. Let's see, 16, 17. 23. Carry the 2. Okay, so 18 and 8 is 26. 27, 28. Carry the 2. So we have 6, 8, 10, 12. All right, we can keep everything since they're all there. We can keep everything here. That means we have 5 significant figures in the answer. Okay. All right. Let's see. Oh, 25. Consider the numbers 2368 and 4.12. The sum of these numbers has so many significant figures, and the product has how many? Okay, let's do the sum first. 2368. And then 4.12. Okay, they're lined up. So we can say 10, 1, 7, 8, and that's 7, 2. So it's 4 significant figures for the sum. How many for the product? The product would be 3 for the product. Why? Because of that right there. That limits the outcome. So it's 4 and 3. D. Okay. (27) Using the rules. Okay, here's a subtract rule. This one should go fairly quickly. We just have to get the numbers up here. 40021 and subtract 0.179. 179. Subtract that. So 0 from that one is 1. That's 3. 7 from 9 is 2. 1 from 9 is 8. 3. So how many can we keep? We have to limit it to that one right there. That's the uncertain. Furthest to the left. So that means it's 3.823. Yeah. Because that's a 1. We just keep that number, 3.823. Okay. All right, okay, here's a combination. 3.478 and 1.164. This is 32. Times 1.164 in parentheses, then divide by 2. And this is grams and this is milliliters. And then what? Subtract 0.169 grams per milliliter. Okay, so what's our order of operation here? PEMDAS, parentheses first. But parentheses, multiply, divide, add, subtract. So we're going to do all of these first. We're going to do this one and that one. So that means we can do all of these together and find out what the outcome of that one is. Right? It's going to have how many significant figures in that portion of the answer. Because that's where we have to determine the answer. 4 here, 2 there, 3 there. So we can only have 3 in our answer. 3.478 and 1.164 times gives me a number. Divide by 2. And this, my calculator says 2.0242. But we can only keep 3 of them. Right? So 2.02. Now we have 2.02 minus 0.169. Okay. 9 from 10 is 1, 6 from 11 is 5, 1 from 9, 8, 1. But we have to restrict it to that one, 1.85 grams per milliliter. Okay. Now that takes care of the mathematical operation. The units of measure are important also. This is grams per milliliter. Remember, you can't subtract apples from oranges, right? So the units of measure have to be the same before you can do the subtraction. And that they are grams per milliliter here, grams per milliliter there. So we're safe. And when you're multiplying units or dividing units, you just keep whatever you got, anything that doesn't cancel. But when you're adding and subtracting, the two factors that are in that operation must have the same units of measure, because there's no way to preserve them in an add and subtract environment. But this one, oh yeah, we've done simple unit conversions with just first power. Now we've got a cubic centimeter, and we're going to convert it to liters, 781.2 cubic centimeters. All right. And we want to go to liters. How do we get there? Well, if we work backwards, we know that there are 1,000 milliliters in a liter. Right? So if we did that, like that, then we have to say this is equal to, like, cubic centimeter is equal to milliliters, 1 to 1. So now all we have to do is divide this by 1,000. Okay. The unit of measure is bigger, the number gets smaller. So we moved it 3 places to the left because we're divide this by 1,000. Divide something by 1,000, you just move the decimal to the left 3 places. Multiply by 1,000, 3 places to the right. How far have y'all gotten in algebra so far? Not very far, right? No. Okay. You'll get to stuff like this pretty soon. So this would be good practice. The pressure of the Earth's atmosphere at sea level is 14.7 pounds per square inch. This is number 37. 14.7 pounds per square inch. That's 1 atmosphere pressure. What's the pressure when expressed in grams per square meter? If we want to go to grams per square meter, we need conversion factors. And using the conversion factors we're given there, centimeters to inches and pounds to kilograms, when you are converting more than 1 unit of measure to get an answer, do 1 at a time, because they're all multiply divide anyway. It doesn't matter what order you do them in. So let's do pounds first. Let's convert pounds to grams. All right, we have 2.205 pounds per 1 kilogram. Getting close. Now we need grams. Right, 1,000 grams per kilogram. There we go. We got our grams done. Okay. Now let's do cubic centimeters. All right, we're gonna go, what's the relationship between, now, this case, inches is on the bottom in the denominator, so inches has to be up here to cancel. And centimeters, yeah, inches and centimeters. So we have 2.54 centimeters per inch. What's wrong with this picture? Centimeters is not squared. Inches is not squared. So here's how you fix that. You square them both. Okay. And that square propagates through this parentheses. That's a square inch, and this is 2.54 squared. Also, square inches and square centimeters. Remember, everything you do to the number, you do to the units. So if we square that expression, we get our conversion factor. And that takes out this one and this one. Okay. It's just that when you do the calculation, don't forget to square that. Okay. So if you have a string, a chain conversion, you can do them in any order. I like to do them numerators followed by denominators. So all you have to do is say 14.7 times 1,000 times 1 squared, which is 1, divided by 2.205, divided by 2.54 squared, 2.54. Then I have to square it, then I can divide by it. So I end up with 1.033.3354 grams per square centimeter. But how many? This is all multiply and divide. So we just use the one rule, which is the smallest one. Well, that's a conversion factor. It's exact number, exact number, exact number. We're only limited by this one, which is 3 significant figures. So if I say 3, if I say 3 from here, 1, 2, 3, it's 1030 grams per cubic centimeter. Oh, it's in sheet. It's in scientific notation. 1.03 times 10 to the third grams per cubic. What's wrong with this picture? Oh, square meter. Why didn't somebody say something? Okay, we're not done. Right. We got this one. Now we have to convert square centimeters to square meters. Right, 1 meter is 100 centimeters. Just square it. Right, square meters, square centimeters cancel. So I still got this calculation up to here. What I need to do now is say would be what? 10 to the 4th. Right? 10 squared, 10 to the 4th square centimeters, which is 10,000, right? Now we have 10333. And we're going to keep 3 significant figures. It can only be 1.03 times 10 to the 4th. 7. Oh. It goes bigger than that. So 1, 2, 3, 4, 5, 6, 7. There you go. Look at my calculator, right? And this is grams per square meter. Which should be B. Yep. Questions? It's always good practice to pay attention to the question. $41. The density of liquid mercury is 13.6 grams per milliliter. What's the density of water? 1 gram per milliliter. 1 gram per milliliter. So mercury is 13.6 times as dense as water. What's the density in units of pounds per cubic inch? This one, in the interest of time, this is another chain conversion where you're converting one, you're converting the other. I'm going to let that one go. It's in your worked problems, I know. But in the interest of time, I think we ought to skip that one. And let's see. Oh, let's do this one. 46. During a physics experiment, an electron is accelerated to 93% of the speed of light. And there's the speed of light, 3.00 times 10 to the 8th meters per second. What's the speed of the electron in miles per hour? Okay, I'm going to do this one because there's a twist, there's a trick to this one. And you have to recognize that 93% of the speed of light is not the speed of light. So we have 3.00 times 10 to the 8th meters per second. Meters per second. And our starting point is 0.97. That's the decimal equivalent of 97%. So that would be our starting point for the speed of light in meters per second. Then you do the conversion to miles per hour, right? And we need to do 1 kilometer is 0.6214 miles. All right. We got to convert this to kilometers. Right. So now we can use our conversion factor, miles per kilometer, 6214. There we go. So now we got miles. We can even convert seconds to hours. How many seconds are in an hour? 60 seconds in a minute, right? And 60 minutes in an hour. So 60 times 60 is 3,600. So, and follow all your units, right? We cancel the seconds, we cancel the meters, cancel kilometers, and we got miles per hour left over. Just run the calculation. And we're starting with 3 significant figures, so we should have 3 in our answer, which we don't. Oh, maybe they're using this as a limiting factor. That must be it. 0.97 proceed. This 0.97 is a limiting factor. So 6.2 times 10 to the 8th miles per hour. Should be what you come up with there. All right, 49. In 1928, 29.3 grams of a new element was isolated from 660 kilograms of ore molybdenite. That's a clue. The element's probably molybdenum. Right here. The percent by mass of this element in the ore was. Okay, so we have 29.3 grams of the element. We need to have the same units in the denominator to find out what its percent by mass is. So how many grams is 660 kilograms? 660 kilograms. We want to convert that to grams. We can do it right here in the denominator. Kilograms, grams, 1,000 there. Oh, times 100, right? Percent. So I'm gonna put in 29.3, and then I'm gonna do this calculation. 660 times 1,000. And then divide it in there and times 100. I get 0.0044%. And this is two significant figures, so we're limited to two significant figures in our answer. Okay. That's percent by mass. Temperatures, 50. Doing on time. Yeah, got about 25 minutes left. 409 Kelvin equals what? So we got choices there. Look at your choices. That also drives the finding the answer. 409 Kelvin could either be Fahrenheit or Celsius. Well, what's the conversion? If you have Kelvin, 409, what do we know is the conversion? We know how to go to Celsius, don't we? So do that one first and look at the Celsius and see if it's one of those. So what do I need to do? Celsius plus 273 is Kelvin. So Kelvin minus 273 is Celsius. All right, so that's 136 degrees C is D. See, we didn't even have to calculate Fahrenheit. We will on the next one. Uh, 51. Let's see, 391 degrees C in Fahrenheit. 391 degrees C. So what's the formula? Remember, it's in useful information, so you don't have to remember it. I just happen to remember. F equals 9/5 C plus 32. And we know what C is, so we just say 9/5 391 plus 32, and that's equal to F. And if we do our math right, it should be 736. Very nice. Is that reasonable? Well, usually the Fahrenheit, when you get to these higher values, then the adjustment of the 0 point becomes less and less important. So if you just want to estimate, say 391, what's 2 times 391? It's about 780. Yeah, we're in the ballpark. Right. 54. Let me see. I think there are some bonuses in this. No, no bonuses in this one. I think the reason I kept bonuses out of the first exam is because this is basic stuff. You got to know it. So in 1984, which is what? Blue smoke. Who cares what year it is? Some drums of uranium hexafluoride were lost in the English Channel, which is known for its cold water, 17 degrees C. So the temperature of the water is 17 degrees Celsius. The melting point of uranium hexafluoride is 148 F. Yeah, that's the melting point. In what physical state is uranium hexafluoride? Well, if it's cold enough, I mean, if it's below, if that temperature is below this temperature in Celsius, then it's going to be solid. You really don't have to do the calculation unless you want to. Equals 9/5 Celsius plus 32. So Fahrenheit is going to be here, 148. We minus 32, which is 116. And then we Flip that over and about half of that is what? 50? 58 is a half, right? So it's definitely colder than the temperature required to keep uranium hexafluoride a solid. It's going to be a solid. Now, if you feel more comfortable actually going through and finding the exact temperature, that's fine. But you'll get the same answer. That's where estimation is a powerful tool sometimes, especially during the exam. If you don't need to know the exact number, just get in the ballpark, then you can answer the question. 56. A monolayer, 3.23 times 10 to the minus 6 oleic acid. 3.23 times 10 to the minus 6 grams of oleic acid. What's oleic acid? It's a fatty acid, right? You get it by busting up true fats. Anybody had anatomy and physiology? No. Biology? Okay. Well, we don't have time to go into that detail, but it's a fatty acid. All right. And if you put a little drop of it, which is a very small amount, on calm water, it'll spread out. In fact, it's spread out to be a monolayer, because fatty acids have a head on them, say, that's hydrophilic. That is, they like water. So this is going to be dissolved in the water. But the tail is hydrophobic. So it's going to be pointing up. So you're going to have this layer of water, and you're going to have these hydrophilic heads here, and those guys like this. The hydrophobic tails are up here, dissolved in each other. Okay, that's why it says it forms a monolayer. It has an area of 20 cubic centimeters. So if we take this circle and rotate it around like that, we're going to get this monolayer, and it's 20 square centimeters in area. Okay. So this many grams is spread over that volume. And we might also need the density, 0.895 grams per mil. All right. What's the thickness of the monolayer? That is the length of the molecule. So if we try to do a three-dimensional depiction of this thing right here, then you've got like this, and this is the length of the monolayer. Well, the monolayer is a cylinder, right? Remember from geometry? What do we do with a cylinder? That's it. Well, if you want to know the volume of the cylinder, you just need to know the area here and the height there. Area times height is the volume. So what's the volume of this oleic acid there? Well, it's the area times the height. The area is 20 cubic centimeters. We don't know what the height is. That's the unknown, right? So the volume equals 20 square centimeters times the height. What we need is the volume. If we can find the volume, then we can solve for that. So far, so good? Okay. So where does this come in? Well, this has volume in it. It also has mass, and we know the mass right here. We also know the density. So this is equal to mass per unit volume, or that mass, 3.23 times 10 to the minus 6 grams per this volume. So that means if we put this volume over here and make this movement, this transition, 0.895 grams per mil. Okay. They just swap places. Bring the V over here and mass over here. And that will give us the volume in what? Milliliters. .23 exponent 6.895. And this is 3.6089 times 10 to the minus 6 milliliters. Okay. So this is the total volume in milliliters. So what's a milliliter? It's a cubic centimeter. We need to put cubic centimeters over here because these units are in centimeters. So if we know that it's, we solve for H is going to be V over 20.0 square centimeters. So the V is 3.6089 times 10 to the minus 6 cubic centimeters divided by 20 square centimeters. These 2 square centimeters cancel 2 of those and leave us with 1. So now all we have to do is the math. And divide by 20. And I get 1.8045 times 10 to the minus 7 centimeters. Is that the length? Yeah. Now, since it's multiple choice, we can just pick out the answer. We know it's D. If we were going to take our significant figures into account, we would say there's 3. We just drop it off there. 1.80 times 10 to the minus 7 centimeters is the length of that tail. That's the height of the cylinder. Everybody's eyes glazing over. And I erase. Right. I'm going to have to come back and finish this recording later. All right. Piece of zinc with a mass of 12.14 grams is submerged in 46.3 cubic centimeters of water in a graduated cylinder. The water level increases to 48, the correct value for the density. All right. So sometimes it helps to draw pictures. All right. First of all, if we're going to calculate density, we need to know mass and volume. So do we know mass? Yes. 12.14 grams. Now we need to know volume. How do we get volume? By displacement. If that cylinder started out at 46.3 milliliters, or cubic centimeters, and we put our zinc in it, then it went up to 48, right? So what volume is that zinc? It's the difference between those two. 7.1, right? 1.7 cubic centimeters. So divide 12.14 by 1.7, and you should get 7.1 grams per cubic centimeter. Does that make sense? 7 times 1 is 7, and then 7 times 7 is 4.9, or about 5. 5 plus 7 is 12. We're good. Okay. Do a little estimating there. Just to check your answer. Does it make sense? All right. Boiling of water is what kind of change? 62. Boiling of water is a physical change, right? But the answers also say why. Well, we know it's not C or D or E because it's not a chemical change at all. So it has to be A or B. Physical change because what? The water merely disappears? No, the water could disappear with a chemical change too. We could turn it into gas. We could turn it into hydrogen and oxygen with a chemical change. But it's a physical change because the gaseous water is chemically the same as the liquid water. Its identity has not changed. That's why B is the answer. Now put this one in here. And there are several, 70 through 73. Because the representation here might be a little difficult to follow. What we've got here is if you have a single symbol, that's an atom. If you have two symbols together, that's a molecule. Okay, that's the way we're representing them. So A looks like it has two different symbols in it. Right? It has an open circle and a grayed circle, and they're very far apart. So that tells me this is a gas, a mixture, a gas mixture. So let's do that. Let's say A is a gas mixture. How about B? B is regularly arranged one type of atom. That's an element, and it's a solid. This is a solid element. This is a mixture of elements. Okay, how about C? C is also a gas. It looks like they're very far apart. This is a molecular gas. How about D? That picture is random mixture. Looks like it's probably a liquid, and it's a heterogeneous mixture of elements. And then E, what's E? E is a regular arrangement of element and molecules. So we have both element and molecule in a homogeneous mixture. Okay, so let's look at 70. Which best represents a homogeneous mixture of an element and a compound? That's E, right? So this one is E. 71 is which best represents a gaseous compound? Right. Molecular gas, C. 72, which best represents a solid element? B. And the last one, which best represents a heterogeneous mixture of two elements? Heterogeneous elements. D. Okay, that's the way you interpret those pictures. $75. Which of the following has a different value on the moon compared to the Earth? Yeah, the weight. The weight is a measure of force in a gravitational field. Mass is fixed. Time is fixed in Newtonian universe, right there. Get close to a black hole and all bets are off. And moles are just numbers of things, right? That's not going to change. So yeah, B, weight will be different on the moon. About 80. Which separation technique is based on differences in volatility of the substance to be separated? What do we mean by volatility? How easily does something evaporate? Right? More volatile means it evaporates at a lower temperature. The EPA has standards on VOC, volatile organic compounds. If you buy a can of paint, look on the side, and it has to display what its composition is in terms of volatile organic compounds. Most household paints that you're going to use indoors are water-based, so they won't have very high organics. But if you use an outdoor paint, like an oil-based paint or some other kind, then it's going to have more volatiles in it. And they're more permitted because it's an outdoor use. Anyway, so what technique would separate a mixture based upon volatility? How about filtration? That's particle size. Right? You filter out larger particles or filter out particles from a liquid that goes through the filter. Distillation. There's it. That's the one. Right? Every moonshiner knows about that. The ethanol, the booze, is more volatile than water. So he just sets his propane burners under the mash tank and hooks it up to his still, and over it comes. Right? Alcohol with only a little bit of water. It always has some water in it. What's the percentage alcohol, the highest percentage alcohol you can get by distillation? 95%. If you want to look it up, the reason it's that is because it forms an azeotrope. In other words, 95% ethanol with 5% water comes over as a single unit. So you can't get any higher than that except by special means. So if you go to the package store and buy some crystal clear for a punch, it has to be made special, 100%. They used to use benzene. Put a little benzene in it, forms a different azeotrope that gets rid of all the water before the ethanol comes over. And then you get clean. Or the way I used to do it in the lab, for small amounts, I would take sodium sulfate, anhydrous sodium sulfate. It had no water in it, but it will absorb water. And I have a bed of it, and I just pour my 95% through it. Actually, I used 100%. But over time, it'll absorb water. So I poured it through there and came out 100%. That's why you don't want to store gasoline for too long, especially if it's got ethanol in it. If it's got ethanol in it, one season is all you can get out of it. If you keep it for the next season, your engine won't start. Your mower won't start. Your leaf blower won't start. Your weed whacker won't start because it's got too much water in it. But the ethanol in the gas absorbs water. And so we put, what's that stuff you put in your gas? It's pink. Can't remember the name of it. Huh? No, it's got another name. You put it in your gas can, and it keeps it from absorbing water and deteriorating. I'll think of it in a minute. How we do it? Got about 4 minutes. Okay, we're up to chapter 2. This would probably be a good place to stop.
Right. Chapter 2.
Pick up where we left off. Chapter 2, number 1. The first people to attempt to explain why chemical changes occur were the Greeks, the ancient Greeks. Now, we recognize that different types of chemistry were occurring much earlier than the Greeks. I mean, from the when man came out of the Stone Age, he came out of it with metal objects. First, it was copper, and then it was copper and tin, which is bronze, and then it was iron for their utensils, for their weapons, and then there was steel. But this was all alchemistry. This was recipes and handed down from generation to generation. The Greeks, when the Greeks came along, they tried to understand and explain why certain things were happening the way they were. Right, so the Greeks get credit for that. The first chemist to perform truly quantitative experiments was Robert Boyle. He's given credit for being essentially the first modern chemist because he was quantitative about his approach, and he designed experiments to answer questions. So Robert Boyle answers that question. The scientist who discovered the law of conservation of mass and is also called the father of modern chemistry. Well, yeah, Robert Boyle. It could be. Now, the answer to 3 is Lavoisier. And there's some evidence for calling him the father of modern chemistry. He was very wealthy, so he had the funds that were necessary to build the instruments that he needed to work his experiments. And his experiments were also quantitative. In fact, he was quantitative not just with solids and liquids, he was quantitative with gases. So, enough said. Lavoisier was considered the father of modern chemistry. So, which of the following, let's see, that was E. Which of the following pairs of compounds can be used to illustrate the law of multiple proportions? Right? Remember, there's a difference between the law of definite proportions and the law of multiple proportions. Definite proportions was proposed by Proust. Multiple proportions were proposed by Dalton, John Dalton. So, which one of these would illustrate the law of multiple proportions? Remember, the multiple proportions, we can explain them today as one element here and another element there. Then if you keep this one the same, the next one is going to be twice as much, and the third one's going to be 3 times as much. So that's the multiple proportions. They're whole number multiples of the lowest mass. So you need 2 elements in both of the compounds, and one of them needs to be a whole number multiple of the other. So if we just go process of eliminations, A can't be it, right? Nitrogen, hydrogen, chlorine. No, we can't add another one. Oxygen and chlorine. No. Oxygen and chlorine again. nitrogen monoxide, nitrogen dioxide. That's a perfect example right there. So that's D. All right, let's make some more room. Ooh, I'm gonna have to treat this board. Let me treat this board before we go any further. Yeah, I'll try to do it without erasing this stuff. That ought to work better. Okay. Yeah, let's move on to the next one. Number 7. A sample of chemical X is found to contain 5 grams of oxygen, 10 grams of carbon, 20 grams of nitrogen. So I mentioned this some time ago. When I approach a word problem, because word problems are designed to confuse, I like to extract the information from the problem and put it in a more recognizable form. So this chemical has 5 grams of oxygen, 5.0 grams of oxygen. It has 10 grams of carbon and 20 grams of nitrogen. Okay. The law of definite proportions would predict that a 70-gram sample of chemical X should contain how many grams of carbon? Remember, definite proportions means that these proportions for that compound are fixed. The masses, the mass ratios of each of the elements is fixed. So no matter where the compound comes from, we have another source of the compound, it's going to have the same ratio. Right? So if we have 70-gram sample of X, how many grams do we have here? 20, 30, 35. This is 35 grams of X. So if we have 70 grams of X, we should have double everything in there to maintain the ratios. So carbon then would be 20 grams, right? Double the total amount, double the component amounts. So the answer is E. That's a little better. Not perfect. All right, 7, 9. Which of the following statements from Dalton's atomic theory is no longer true according to the modern atomic theory? Okay. Elements are made up of tiny particles called atoms. That's still true. No problem there. Atoms are not created or destroyed in chemical reactions. That's true. All atoms of a given element are identical. That's false. They're not identical because of isotopes. So C is false. That means D and E should be true. Atoms are indivisible in chemical reactions. That's true. All of these statements are true according to the modern atomic theory. Well, that one's not true. So that's a problem with this question because we have 2 false ones. All atoms of a given element are identical. All these statements are true. No, they're not all true. Right? So C is the best answer, But E works also, because it says all of them are true, and they're not all true. All right, I have to work on that one. The chemist credited for inventing a set of symbols for writing elements and a system for writing the formulas of the compounds and for discovering selenium, silicon, thorium is. Now, we did not discuss this one in class. You would have had to read this one in your textbook. But the person responsible for that is Berzelius. Berzelius was I think he was a Swedish chemist, and he proposed simply using letter symbols for the elements. Now, there were some floating around that were pretty wild. And do you remember when I showed you the picture of the different symbols that alchemists used? They were derived from those. John Dalton was in favor of those weird symbols. I'm glad Berzelius won. We decided to use his system. Avogadro's hypothesis. Avogadro's hypothesis states that if you have two volumes of gas, and they don't have to be the same gas, two volumes of identical volume at the same temperature and at the same pressure, you will have the same number of particles in each one, the same number of moles of gas in each container. Now, which one of these statements satisfies that description? Each atom of oxygen is 16 times more massive than the atom of hydrogen. No, his hypothesis didn't say anything about that. A given compound always contains exactly the same proportion of elements by mass. Now, that's definite proportions. That was Proust. When two elements form a series of compounds, the ratios of masses that combine with 1 gram of the first element can always be reduced to small whole numbers. That's Dalton's law of multiple proportions. D, at the same temperature and pressure, equal volumes of different gases contain an equal number of particles. That's it right there. Mass is neither created nor destroyed in a chemical reaction. That's Lavoisier. So D is the correct answer for Avogadro. 13. The first scientist to show that atoms emit any negative particles was J.J. Thomson, using his cathode ray tube. Many classic experiments, number 14, have given us indirect evidence of the nature of the atom. Which of the experiments listed below did not give the results described? Okay. A says, Rutherford's experiment proved the Thomson plum pudding model of the atom to be essentially correct. No. Rutherford's gold foil experiment drove a stake through the heart of the plum pudding model. So, and I'm not sure, I don't think this may have been the same Thomson, I don't think it was, as discovered the electron. I think it was a different Thomson. But the model was laid to rest by Rutherford's experiment. A is false. And that means the rest of them should be true. Well, except for all of the above experiments gave the results described. No, they didn't. The electric discharge tube proved that electrons have a negative charge. Yep. Millikan's oil drop experiment showed the charge on a particle was a simple multiple of the charge on the electron. Yes, he did. And B, Rutherford's experiment was useful in determining the nuclear charge on the atom. Yes. Why? Because atoms are neutral. And if you know the negative charge, you have to have enough positive charge in the nucleus to balance it. 15. Oh, this was, what was that? A. 15. The scientist whose alpha particle scattering experiment led him to conclude. Okay, we just talked about him. That was Ernest Rutherford. All right, let's see. Yeah, 16. Alpha particles beamed at a thin metal foil may what? This is still Rutherford's experiment. If we beam alpha particles at the foil with the nuclear atom, most of them will go straight through. They'll pass through directly. They'll pass through without changing direction. B, they'd be slightly diverted by attraction to electrons. Yeah, that's true. They'd be reflected by direct contact with the nucleus. Yes, all three of those are true. So E is the correct answer. All right. 17. Which one of the following statements about atomic structure is false? All right. 17. An atom is mostly empty space. That's true. Most of the mass of an atom is in the nucleus, and the electrons occupy all the other space. Almost all the mass of the atom is concentrated in the nucleus. Yes, A and B are both true. The protons and neutrons in the nucleus are very tightly packed. That's definitely true. The number of protons and neutrons is always the same in the neutral atom. No. For the lighter atoms, yes, you will have the same number of protons as neutrons, like helium. Right? Helium has 2 protons and 2 neutrons, giving it a total of 4 for the mass number. But when you get to larger atoms, let's see, let me look at an example. Let's try zinc. 35 protons and no, 30 protons and 65. 65 mass number. So that would be 35 neutrons. Right? So you don't have the same number. And as the atoms get bigger, I'll just throw this one in for free. As the atoms get bigger and heavier, the number of neutrons balloons. It takes many, many more neutrons to stabilize a nucleus as it gets bigger. Because think about it. If you got all those positively charged protons crammed tight together, they're pushing against each other. Right? So what you need is a strong force to hold them together. And one school of thought says that's the purpose of the neutron, to hold the nucleus together. Okay, so D is the correct answer, right? That is a false statement. All right, number 20. Let's erase some of this stuff. Sure, I'm still centered. Yeah, okay. Number 20. Which of the following atomic symbols is incorrect? All right. So if we look at each one of these symbols, the place that I would start is with the, let's take the first one, carbon. It says carbon has 6 protons. And we know that the symbol, the element, and the number of protons go together. If you know one, you know the other. So you look at your periodic table and say, okay, carbon, yes, carbon has 6 protons. Okay. So we look at each one of them and see which one of them is incorrect. We don't have to pay attention to the mass number yet. So carbon is correct. Chlorine has 17 protons. That's correct. Just look it up in your periodic table. Phosphorus has 15 protons. Yes. Potassium has 19 protons. Nitrogen has 7 protons. That one is false. That's as far as we need to go to answer the question, right? 8 protons in nitrogen is wrong. 8 protons is oxygen. All right. So number 20, E is the false one. All right, 21. The element rhenium exists as 2 stable isotopes, 18 and 18 unstable isotopes. Rhenium-185 has in its nucleus, right? A lot of that is unnecessary. All we need to know is rhenium. Let's see, this is 21. And all we need to know is the symbol and 100, and rhenium has 185. Let's see. There's 2 stable isotopes and 18 unstable. Rhenium-185 has in its nucleus. When we write it like that, rhenium, when we write it like this, 185, this is the mass number, protons plus neutrons. So how do we find out, since the answers are numbers of protons and numbers of neutrons, how do we find out how many protons it is? Periodic table. Look for rhenium. Let's see, where's rhenium? I don't find it too often. There it is. It's underneath manganese, technetium, and then rhenium. 75 protons. So 110 neutrons. So 75 and 110 is D. That's your answer. All right, let's see. 22. Which among the following represent a set of isotopes? Okay. We're looking at Roman numeral 1 through 5. And we want to look at each one and see which one is an isotope of the other one. Or there could be 3 of them. We don't know. Let's see. Which ones have the same number of protons? Well, 1 and 4 have the same number. Let's see, this is 22. 1 and 4 have the same number of protons and different neutrons. Okay, so that works. 2 and 5 have 21 protons and different neutrons. Right, so those are isotopes. And Roman numeral 3 doesn't have a counterpart, right? So only 1 and 2, 1 and 4, and 2 and 5. So that's D. D is the answer for this one. Let's see, we'll skip a few. Come down to 28. A species with 12 protons and 10 electrons is. All right. So if we've got 12 protons and 10 electrons, you know right off that it's an ion. So magnesium, D, can't be it. It's not an ion. But we can't find out what the symbol is because we know there are 12 protons. Look at the periodic table, and we find that 12 protons is magnesium. Right? But it's only got 10 electrons. So what's the net charge? You got 10 negatives and 12 positives. You have 2 excess positives. So there you go. It's C. That is your answer. Number 29. The number of protons, neutrons, and electrons in 19 potassium ion 1939. Okay. The number of protons, easy. That's 19 protons. Okay. How many neutrons? 19 plus 39 is 20. How many electrons? You got one fewer electrons than you do protons because there's an excess of one proton. So the electrons are 18 electrons. Okay, so E is the answer. Okay, now we're going to look at some symbols, right? And match them up with either their symbols and names or groups in the periodic table. This first one is references groups. So which one of these is incorrectly paired? So you need your periodic table and you look for SR, which is strontium. Is it an alkaline earth? Yes, it's in the second column. That's an alkaline earth. Ta, tantalum. Is it a transition metal? We just look for Ta. Where is it? Let's see. Ta. Ta. I don't look for it very often, so I have to really search. Tantalum. Transition metal. I'm looking straight at it and don't see it. Where is it? There it is. It's under vanadium. Vanadium, niobium, tantalum. Yeah, it's a transition metal. That's true. Okay, how about F? Is F a halogen? Yeah, it's the first halogen. It's on the second one from the right. Noble gases, then halogens. D, H. Hydrogen is a noble gas? I don't think so. Hydrogen's off by itself. And the other one, ruthenium, is a transition metal. You can find it in that middle group. So the false one is D. Hydrogen is not a noble gas. 34? Yeah. How about pairing these symbols with their names? Phosphorus. Is PR phosphorus? PR is protactinium, I believe, if I'm not mistaken. Let me check just to satisfy myself. Let's see. Nope. PR is praseodymium. But phosphorus is just P. That's it, just P. So that was false. We found our answer. The rest of them should be correct. Palladium is PD, platinum is PT, lead PB, potassium K. Those are all correct. So that was A was the false one. 35. False one here. Copper, is that Cu? Yep. Cuprum. Carbon, C? Yep. Cobalt, CO? Yep. Calcium, Ca? Yep. Cesium, Ce? No. Cesium is Cs. Ce is cerium. Let's see. Cerium is a lanthanide. It's in one of those bottom rows. So E is the wrong one. Which of the following are incorrect? Okay, let's try these. Antimony, is that SB? Yeah. SB stands for stilbium, which is Latin. Silicone, Si, yep. Silver, Ag for argentum. Argon, Ar, yep. Astatine, As. No, astatine is At. As is arsenic. So E is incorrect. Let's see, 37. Yeah, we're going to do 37 also. All the following are characteristics of metal except, right? Metals are excellent conductors of heat. Yep. They're malleable. That is, you can shape them. They're ductile, which means you can stretch them into a thin wire. A, B, and C are all true. D, they're often lustrous. They're only lustrous if they're solid masses that have been polished. But that's why we say often lustrous. Yes, true. That's true. They tend to gain electrons in chemical reactions? No. Metals tend to lose electrons in a chemical reaction. So E is the false one. Let's see, skip a few. How about 41? You're given a compound with a formula M standing for metal, Cl2. MCl2, okay. In which M is the metal, you're told that the metal ion has 26 electrons. So if this has 26 electrons, what's the identity of the metal? What we have to find out is how many protons does it have? Well, if this metal has 2 chlorines, and halogens always form a -1 charge. So this -1 charge times 2 is 2 minuses. Okay? That means this one has to be a 2 plus to balance it. That means we need 28 protons to give you that 2 plus charge. And 28 protons is nickel. Okay? So E is the correct one for 41. All right. Back over a little bit. Let's see, who's next? 45. How many oxygen atoms are there in one formula unit of Ca3PO42? Ca3PO42. First of all, is that written correctly? Right? This is going to be a type 1 compound because calcium has a fixed charge being an alkaline earth. So it has a 2 plus charge. And this is a polyatomic ion. You can tell by the parentheses. PO4 has a 3 minus charge. So 3 comes over here, 2 goes over there. That's good. Okay, now the question is, how many oxygen atoms are there? Well, there are 4 in this group, but there are 2 groups, right? So we have 8 oxygen atoms. D is the answer. Now we're going to name some compounds. All right, 47. Name this compound. Okay. We know it has iron in it. We know it has oxygen in it. So it's iron oxide. But it has a metal in it. That means it's either a type 1 or a type 2. So which one is it? Does it have a fixed charge or multiple possible charges? Iron is an alkaline, is a transition metal. So it has multiple possible charges. Oxygen is a chalcogen with a -2 charge. This one has to be a 2 plus charge. That means It's a 2+ charge for this iron oxide. That makes B the answer. The correct name for Ca2+. Remember, when we name something in chemistry, it has to be unambiguous. There's no mistaking the name for some other species, and it's not redundant. So we know this is calcium, and that it's an ion. Do we need to say any more? No. Calcium is an alkali metal. Alkaline earth. Alkaline earths have a 2+ charge. That's all they have. So if we say calcium ion, it has to be that. Can't be anything else. And we don't have to put the charge in there because it can only have that charge. So if you put B, you're wrong. If you put A, you're also wrong because it's an ion. C is the answer, calcium ion. And you don't say monocalcium either. That's redundant. 51. All right. What is the subscript of barium in the formula barium sulfate? All right. Barium we know is this. And sulfate is a polyatomic ion with a 2- charge. Barium is an alkaline earth, which means it's in the second column. It has a 2+ charge. So we need one of these and one of those. That's it. So what's the subscript of barium? It's understood to be 1. We don't write the 1 in, right? Why? Because if you got the symbol there, you got at least 1. So why write 1 in there when you've already got the symbol? A is the answer for 51. 53. We're looking for the formula for sodium dihydrogen phosphate. So we know we have sodium. Dihydrogen phosphate is a polyatomic ion. You can look it up in that list. It's dihydrogen phosphate. And what's the charge on it? The charge is a -1. Sodium is an alkali metal. It's always +1. That's the formula right there. A is the answer. All right. '56. See, keep this thing centered. There we go. All the following are in aqueous solution. Which is incorrectly named? All right. Notice one thing about all of these compounds. They start with hydrogen. And if they're in aqueous solution, then we're talking acids. All right. So which is incorrectly named? Well, remember the first rule is, are there hydrogens in the first part of the formula? And is it an aqueous solution? That makes it an acid. Second is, are there any oxygens there? If there are oxygens, then you don't say hydro. If it's missing oxygens, you say hydro. Okay? So, the first one is formed from the sulfate ion. Eights become X. So sulfuric acid is correct. H2CO3. CO3 is another polyatomic ion that's carbonate. Eights become X. Carbonic acid is correct. H3PO4. Right? PO4 is phosphate. 8 becomes Ic. Phosphoric acid. That's correct. HCN has no oxygen in it. So we start the name with hydro. And we say hydrocyanide becomes ick. Ide becomes ick. Hydrocyanic acid. That one is incorrect. We're missing the hydro. And the last one, hydrochloric acid, is correct. So D is the one that's wrong. That's the incorrect, the named one. Okay, we've got some more. Let's see. We have oxygens in all but B. So in the interest of time, look at the one that has no oxygen in it, HBr. It should be hydrobromic acid. Instead of hydrogen bromide, it's bromide, it becomes ick, hydrobromic acid. So B is the incorrect one. And you can work your way down through the others and find that they are all from polyatomic ions and are correctly named. Oh, wait a minute, that was not even highlighted. So you got that one for free. All right, let's stick with the highlighted ones here. Which of the following are correct? All right. How about the first one? Is S2 minus sulfide? Yeah. Right. Pair it with any metal, it's metal sulfide. How about ammonium chloride? Is that correct? NH4 is ammonium. And chlorine becomes ide. Chlorine becomes ide. So ammonium chloride is correct. HC2H3O2, we have to assume that it's an aqueous solution. Acetic acid, because C2H3O2 is acetate. And we have a hydrogen to start with. Otherwise, it would be hydrogen acetate. BaO, barium oxide. That is correct. So all of them are correct. All right, now we've got to fill in a table. This is 61. All right, our table has symbols. Symbols, number of protons, neutrons and electrons, neutrons, electrons, and charge. Okay. All right, how many? We have 4 places here. So we have that, 2, 3, and 4. Okay. So the ones that we're given are in black, and the red ones are, this is a key, so the red ones are filled in. But we're gonna work them out. All right, we're not just gonna memorize these numbers. 206 PV. 206 P is given. 31 and 38 for the next one are given. And 3 plus charge. Then the third row is 5275 and 54. Okay. And then this one is given Mn2 plus, oops, my mistake. Put that one in the wrong place. Mn2 plus, there we go. And we're also given 30 here and 2 plus down here. Well, that makes sense. This charge is already given. Okay. So that symbol has no charge on it. So we know that the net charge is 0. So how many protons does it have? We look up lead. Lead has 82 protons. Let's use a different color. Well, take me too long to dig it out. 82 protons. 82 from 206 is 124 neutrons. We have no charge, so the number of protons equals the number of electrons. Okay? 31 protons. We look that up. 31 protons is gallium. And let's see, the charge is 3 plus. That means we have 3 extra protons. And we're deficient by 3 electrons. So that means 28 electrons. Okay? 52 protons is 52 tellurium. Does it have a charge? Well, it has 2 extra electrons. So yes, it does have a charge. And then finally, manganese has how many protons? Well, we look up manganese in the periodic table, and it has 25. Yeah. It has a 2 plus charge, which means it has 2 more protons than electrons. So electrons are 23. Okay? That's how it's done. Now, we use the same kind of reasoning for this table. So I'm not going to go through this one. This is, I'm going to leave that one to you. How about the symbols for each one of these? If you've been using your flashcards, then you should be able to rattle these off in your sleep. Right? Silver is Ag. Calcium is Ca. Iodine is capital I. Copper is capital C and little u. Phosphorus is P, capital P. If there's only one letter, it's capital. If there are 2 letters, the first one's capital, second one is small. These compounds. All right, let's do those. A, B, C, and D, and E. Okay. We're going to name the compounds. Oops. My mistake. I think that's right. Yeah. Okay. So we use our flow chart if you want. What do you look for first? Metal. The metal in this one is a transition metal. It has the possibility of multiple charges. So it's a type 2 compound. But the anion position is occupied by a polyatomic ion. So you have to use that name only. So this one is iron for that. Sulfate for the polyatomic. And what's the charge? Well, this is a 2 minus charge. That means this one has to be a 2 plus. Just like that. Okay? Again, we have a metal, but this one is a type 1. Sodium is an alkali metal, and it only has 1 positive charge. So we don't have to say what the charge is, but we do have to find out what this is. That's a polyatomic ion acetate. So it's just sodium acetate. Unambiguous, not redundant. Potassium only has 1 possible charge. It's an alkali metal. NO2 is a polyatomic ion. If you've got oxygen in there, always suspect polyatomics. There are only a couple of polyatomic ions that don't have oxygen in them. So this one is nitrite, potassium nitrite. This one is calcium, which is always a 2+ charge. And this is hydroxide. That's it. That's all you need. Nickel is possible multiple charges because it's a polyatomic ion. I mean, I don't know why I said that. Nickel is a transition metal. So we just say nickel. And then we say carbonate. You look up carbonate, it's a 2- charge. So this one has to be a 2+ charge. Nickel 2 carbonate. All right. All right, 65. All right, well, that one kind of got hidden up there. So 65A, nitrate ion is NO3 minus. That's a polyatomic. You can find it in the list. Aluminum oxide. Aluminum is one of those metals that has a fixed charge. It's always 3+. All right, so we write aluminum and then oxide. Oxide, when it's in an ionic compound like this, always has a 2- charge. This one has 3+ charge. So we put a 3 over here and a 2 over there. Al2O3. Ammonium ion is a polyatomic ion. That's it. Just look it up. Perchloric acid. All right. Has an oxygen in it, so we don't say hydro. And HClO4, this is the perchlorate ion. So 8 becomes ic. Hydrogen ClO4 is perchloric acid. We should write this also to be complete. And the last one, copper 2 bromide. Well, that tells us that copper has a 2+, and bromide is a halogen. It's always -1. So that means we need 2 of them. You don't have to put the charges in to write the compound, but I just leave them there because it helps me balance the charges. And then you can name these compounds. So we've either got a type 1, type 2, type 3, or an acid. Those are the only possibilities that we've looked at so far. Aluminum has a fixed charge. Al2SO4, taken 3 times, is aluminum sulfate. SO4 is a sulfate polyatomic. NH4NO3 is 2 polyatomics. Ammonium nitrate. This one we didn't talk about in class. Hydrogen, when hydrogen is first, it will assume a +1 charge. But when it's second and it's with a metal, then the metal is positive and the hydrogen is negative. So we say sodium hydride. Hydrogen change the ending to IDE. Sodium hydride. K2CR2O7. CR2O7 is a polyatomic ion. It's dichromate. And potassium has a fixed charge, So we just say potassium dichromate, period. That's it. Number 7 is a nonmetal and a nonmetal. So now we have to say how many of each one are in the compound. There's only one carbon, so we just say carbon. And tetra is the prefix for 4. Tetrachloride, carbon tetrachloride. AgCl. Now, silver is a transition metal, but it's also a fixed charge. So it gives you a type 1 compound. Remember, silver, cadmium, and zinc are all fixed charges. Silver is a +1 charge. So silver chloride is the correct name. Calcium sulfate, 1 calcium 2+ balances 1 sulfate polyatomic at 2-. We only need 1 of each. And then HNO2, NO2 is nitrite, and ites become us when we name an acid. So it's nitrous acid. Oops, we got 2 more. Nitrogen and oxygen are both nonmetals, so we have to say how much of each one is there. Dinitrogen, trioxide. And then the last one, tin, will give us a type 2 compound. So we have to say iodine. Iodine is always -1. So that means 2 times -1 is 2 minuses. That means this one has to be 2+. So we say tin 2 iodide. All right, when we write these compounds, you will have the polyatomic ion. You'll have a periodic table and a polyatomic ion list. So you can look them up. You have to recognize that you've got a polyatomic. So see, sodium thiosulfate, right? If this were a binary compound, you would have an element there in place of the thiosulfate, but there's no element by that name. So that immediately tells you this is a polyatomic ion. So look it up. S2O3 with a 2- charge. So sodium has a 1+ charge. Sodium thiosulfate. Sodium with its 1+ charge and thiosulfate with its 2- charge means you need 2 sodiums. Iron 3 oxide. Iron 3+, and oxide is a chalcogen with a 2- charge. So we put a 2 over here and a 3 over there. Fe2O3. Dichlorine heptoxide. You should recognize that as 2 nonmetals. So we need 2 chlorines and 7 oxygens. Cobalt 2 chloride. Right? Cobalt has a 2+ charge. Chlorine is a halogen with a -1, so we need a 2 down there. Aluminum hydroxide. Hydroxide is a polyatomic ion with a -1 charge. Aluminum always has a 3+ charge. So you need 3 hydroxides. The key here is you can't change the subscripts of polyatomics. You have to put a parentheses around them and say how many there are. That's because that negative charge does not belong to hydrogen or oxygen. It belongs to the whole group. So in order to get multiples of that negative, you have to multiply the whole group. That's what the parentheses are for. H2SO3. SO3 is sulfite. Ite becomes us. So it's sulfurous acid. Nitric acid, nitrate, 8 becomes ic. Nitric acid. Phosphate, 8 becomes ic. Phosphoric acid. Acetate. Now, you're going to see it in your textbook like this. C2H3O2. But the other one I put in there because you may see it this way in older publications. Usually, you're going to see CH3COOH. It's the same compound. This gives you a little information about the structure. Right? If we expand that structure, that carbon has 3 hydrogens on it. Right there. And then this carbon is attached to another carbon here. And then this oxygen is here, this oxygen is here, and there. That's your acidic hydrogen. That's the one that dissociates to give you the acid solution. Okay, and phosphorus trichloride. 1 phosphorus and 3 chlorines. That's it. '86. Which of the following, 86, which of the following statements is consequence follows from the law of definite proportions? Okay, that's where the ratio, the mass ratio of all elements are exactly the same for a compound, no matter what the source. All samples of chlorine contain 35 Cl and 37 Cl in the same definite ratio. No, that's not it. We're not talking about isotopes here. The mass of oxygen that is combined with a fixed mass of nitrogen in each of the binary nitrogen oxides can be expressed as a ratio of small whole numbers. That's multiple proportions. C, the atomic masses of all the elements in the periodic table have fixed values. No. That's not the law of definite proportions, and it's not true. The percent lead by mass in the compound galena is the same for all pure samples obtained from any source. That's your answer. Definite proportions. Multiple proportions. Let's see, which one would be multiple proportions? That was B, where we have nitrogen oxides. We have NO, NO2, NO3 as examples. 88. Which of the following elements does not have a symbol taken from the Latin name for the elements or one of the compounds? Iron is Fe, ferrum. Copper is Cu, cuprum. Sodium is Na, natrum. Potassium is K, calcium. Titanium is Ti. That's your answer. Number 90. Which of the following ions is not likely to form from the appropriate atoms? All right. It's not that it couldn't happen. It's just not likely to happen. Which ones? So by process of elimination, we want to find the ones that are definitely going to happen. So if we start from the bottom, sodium is an alkali metal. It's always sodium plus 1. Titanium 4 plus. Now we don't know. So what we have to do is look at the periodic table and see those charges. And yes, titanium 4 plus is possible. And it's very likely. Although it's not the only one, it is possible. Magnesium 2 plus is correct since it's an alkaline earth. Arsenic 3 minus, right? So we have to look at where does arsenic occur in the table. Well, arsenic is a pnictogen. Remember? So Noble gases are 0 charge. Halogens are -1 charge. Chalcogens are -2 charge. Pnictogens are -3 charge. Right. So nitrogen, phosphorus, arsenic, antimony, bismuth typically form a 3+ charge. A 3- charge, excuse me, 3- charge. So by process of elimination, carbon is probably the least likely to form a 4+ charge. It can definitely form a 4+ charge, but it's the least likely. That's kind of a trick question, actually. 91. How many protons, neutrons, electrons in that order are present in the anion formed by one atom of this? It says the anion. What is the anion of iodine? It's a halogen. It's always a -1. So if it has 125 here, how many protons? Well, we look up iodine and it has 53 protons. So 53 protons. What's next? Neutrons, 53 from 125. That's 272 neutrons. Okay. Well, by process of elimination, we could answer it right now. But if we calculate it, we need one extra electron. 54 electrons gives us a -1 charge. So 53, 72, and 54 is D. Let's see. How about this one? 94. Which of the following has 23 protons, 18 electrons? That means it has an excess of protons. How many? Well, 18 from 23 is 5. So it has a 5+ charge. And it has 27 neutrons. So 27 plus 23 is 50, right? So the symbol for 23 protons should be vanadium. Vanadium. There we go. Right. Well, the symbol, they don't put the protons in there, so C is the correct answer. 50 mass number and 5+ charge. Let's see. 95. Which of the following compounds is incorrectly named? All right, we have unique answers, unique for each one of those. We don't have any of the squirrely ones, like 2 of the above, none of the above, and all that. So we can start at the top and work our way down and find the wrong one and stop. MgO2, MgOH2. Okay. So this is a type 1 compound because magnesium is an alkaline earth with a +2 charge. That's a polyatomic ion with a -1 charge. So the charges are balanced. But we only have to name the magnesium. It's a metal. So that's all we have to say. And then we have hydroxide. Magnesium hydroxide. Right? A is wrong. It's not dihydroxide. So we can stop. The rest of them are correct. That's it. Okay, so there's useful information. Should have polyatomic ions and the periodic table. There we go. Okay, so you will have all that information on the exam, all that useful information. All right, that's it for our review for exam 1, chapters 1 and 2.